The following content is provided under a Creative Commons license. Your support will help MIT OpenCourseWare continue to offer high-quality educational resources for free. To make a donation or view additional materials from hundreds of MIT courses, visit MIT OpenCourseWare at ocw.mit.edu.
Thermodynamics. All right, let's start. Thermodynamics is the science of the flow of heat. So thermo is heat, and dynamics is the motion of heat. Thermodynamics was developed largely beginning in the 1800s, at the time of the Industrial Revolution. It's the taming of steel, the beginning of generating power by burning fossil fuels, the beginning of the problems with CO2 in the atmosphere, global warming. In fact, it's interesting to note that the first calculation on the impact of CO2 on climate was done in the late 1800s by Arrhenius, beginning of the generation of power, moving heat from fossil fuels to generating energy, locomotives, etc. So he calculated what would happen to this burning of fossil fuels, and he decided in his calculation, he basically got the calculation right, by the way. But he came out that in 2,000 years from the time that he did the calculations, humans would be in trouble. Well, since his calculation, we've had an exponential growth in the amount of CO2. And if you go through the calculations of people have done these calculations throughout time since Arrhenius, the time that we're in trouble, 2,000 years, and the calculation has gone like this. And so now we're really in trouble. That's for a different lecture. So anyway, thermodynamics dates from the same period as getting fossil fuels out of the ground. It's universal. Turns out everything around us moves energy around in one way or the other. If you're a biological system, you're burning calories, burning ATP, you're creating heat. If you're a warm-blooded animal, you need energy to move your arms around and move around. Mechanical systems, obviously cars, boats, etc. And even in astrophysics, when you talk about stars, black holes, etc., you're moving energy around, you're moving heat around, and you're changing matter through thermodynamics. And the concepts of thermodynamics have even been applied to economics, systems out of equilibrium, like big companies like Enron, completely out of equilibrium, crash and burn, right? You can apply thermodynamic or non-equilibrium thermodynamics to economics. It was developed before people knew about atoms and molecules. So it's a science that's based on macroscopic properties of matter. Since then, since we know about atoms and molecules now, we can rationalize the concepts of thermodynamics using microscopic properties. And if you are going to take 562, that's what you learn about. You learn about statistical mechanics and how the atomistic concepts rationalize thermodynamics. It doesn't prove it, but it helps to gain more intuition about the consequences of thermodynamics. So it applies to macroscopic systems that are in equilibrium and how to go from one equilibrium state to another equilibrium state. And it's entirely empirical in its foundation. People have done experiments through the ages, and they've accumulated the knowledge from these experiments, and they've synthesized these experiments into a few basic empirical rules, empirical laws, which are the laws of thermodynamics. And then they've taken these laws and added a structure of math upon it to build this edifice, which is a very solid edifice of thermodynamics as a science of equilibrium systems. So these empirical observations then are summarized into 4 laws. OK, so these laws they're really deep pillars. They're not proven, but they're not wrong. They're very unlikely to be wrong. let's just go through these laws, okay, very quickly. There's a 0th law. The 0th law, every one of these laws basically defines a quantity in thermodynamics and then defines a concept. The 0th law defines temperature. That's a fairly common sense idea, but it's important to define it. And I call that the common sense law. Okay, so this is the common sense law. The first law ends up defining energy, which we're going to call U. And the concept of energy conservation. Energy can't be lost or gained. And I'm going to call this the you can break even law. You can break even. You don't lose energy. You can't gain energy. You break even. The second law is going to define entropy. And it's going to tell us about the direction of time, something that conceptually we clearly understand, but it's going to put a mathematical foundation on which way does time go. Clearly, if I take a chalk like this one here and I throw it on the ground and it breaks in little pieces, if I run the movie backwards, that doesn't make sense, right? We have a concept of time going forward in a particular way. How does entropy play into that concept of time? Okay. And I'm going to call this the you can break even at 0 degrees Kelvin law. Okay? You can only do it at 0 degrees Kelvin. The third law is going to give a numerical value to the entropy. And the third law is going to be the depressing one, and it's going to say you can't get to 0 degrees. Okay, these laws are universally valid. They cannot be circumvented. Okay, so thermo is also a big tease, as you can see from my descriptions of these laws here. It makes you believe initially in the feasibility of perfect efficiency. Right? The first law is very upbeat. It talks about the conservation of energy. Energy is conserved in all of its forms. You can take heat energy and convert it to work energy and vice versa. And it doesn't say anything about that you have to waste heat if you're going to transform heat into work. It just says it's energy. It's all the same thing, right? So you could break even if you were very clever about it. And that's pretty neat. So in a sense, it says, you know, if you wanted to build a boat that took energy out of the air, out of the warmth of the air, to sail around the world, you can do that. Right? And then the second law comes in and says, well, that's not quite right. Right? The second law says, yeah, energy is pretty much the same in all its form. But if you want to convert one form of energy into another, if you want to convert work, and heat into work with 100% efficiency, you got to go down to 0 degrees Kelvin, to absolute zero, if you want to do that. Otherwise, you're going to waste some of that heat somewhere along the way, some of that energy. Okay, so all right, so you can't get perfect efficiency, but at least if you were able to go to 0 degrees Kelvin, then you'd be all set, right? You just got to find a good refrigerator on your boat, and then you can still go around the world. Then the third law comes in, and that's the depressing part here. It says, well, it's true, if you could get to 0 degrees Kelvin, you'd get perfect efficiency. But you can't get to 0 degrees Kelvin. You can't. Right? Even if you have an infinite amount of resources, you can't get there.